So before we kind of cap off this unit on area, we're going to talk about calculating area in terms of y. We had done x previously, and our kind of idea for that was ceiling minus floor. We did kind of like a top function minus a bottom function. And the prevailing idea when we do things in terms of y, which is the other direction, the other variable, we do right minus left. And we actually change the variable to be a y variable, and that, and, you know, at the end there with the dy. And so that means that everything that goes in the integrand also has to be in terms of y. So if we look at example 6, this one asks us to find the area bounded by x equals 3 minus y squared and x equals y plus 1. Now, we're not used to seeing equations given to us in this format. Usually they are y equals format, but that doesn't mean that we can't figure this out. So I do want to kind of introduce the idea of like the parent function for quadratics. X equals y squared is just a parabola turned sideways like this. Okay, so you can think of this side, you know, the positive direction of the x's. This is kind of like the opening up, except it's opening to the right. Okay, so if we have 3 minus that function, we're going to flip it the other way, and we're going to move it to the right 3 units. Okay, so let me kind of put this back up here. So x equals y squared is graphed at the top. That actually is just a little helpful for our question. So we're going to move it, the positive 3 means we're going to move it up 3 units, but again, thinking of that x-axis kind of like the up that we would normally do. And then the minus part of it means we're going to flip it backwards, right? So wait a second, I'm not doing that right. So something like this, and then I would probably label it, and then x equals y plus 1. I'm going to do that in a different color, of course, and we can think of that like I'm going to solve for y, so that this is x minus 1 equals y, and then more normally graphed, right, would be y equals x minus 1. So that we would graph like normal, so its y-intercept is -1. Slope is up and over 1, and this is the graph that we get. And the region bounded, right, is obviously this yellow space in here. So my job is to figure out how much yellow space there is there. And like I said, we're going to do right minus left, or if you picture yourself in a classroom where the windows are on the right-hand side, so we're going to do window minus wall, and we're going to kind of think of that as we make this calculation. So just a fun little music clip to sneak on you guys. So let's go ahead and the right function, of course, is 3 minus y squared. So I'm going to do 3 minus y squared and then minus sign, and the red function I'm going to put next. But I can't put it in there as x minus 1. Right? Because it's got to be in terms of y. So I'm going to clean that up a little bit, and instead I'm going to put it as the original way that it was stated to me in the x equals format. X was equal to y plus 1. Okay? And since things are switching from right minus, from ceiling minus floor to right minus left, we are also going to switch these limits. So this is a lower intersection, and this is the upper intersection point, because these must be y values, right? When we did area in terms of x, we used x values as our limits. So now, because we're doing area in terms of y, we're going to have to use y values. Okay, so I'm going to put, actually, let me kind of do what I did before. Let's do green on the bottom, orange on the top, and my job is to figure out what the y value of each of those 2 points is. So we're going to do that same way we did previously. We're going to find the intersection point. So I'm going to take 3 minus y squared, and I'm going to set that equal to y plus 1. So you'll notice I'm taking the x equals versions and setting those equal to one another. And kind of like we did the other day, I'm going to add y squared to both sides, keeping the plus y. And then I'm going to subtract 3 from both sides, and I get minus 2. And then when I factor it, I think I'm getting this. And my solutions are -2 and +1. And we should kind of see those y values that we solve for matching what I view in the picture. So this is my y value of -2 as my lower intersection point, right? And this +1 is the y value of the upper intersection. So I'm going to put those here and here. Okay. And that's my setup. Now, to keep this video nice and short and sweet, you know, this ends up equaling 9/2 if you were to work it out by hand. Again, the current objective is just to work on figuring out how to set up these integrals, do things with the y variable. It's not necessarily to do the integration by hand. Okay, but don't be alarmed if I ask you to do that. Okay. Number 7 is a little bit more complicated of a graph. So we've got x equals y squared, which I tried to mention before, right? Is this parabola turned sideways. And then we kind of have this like more complicated version here. I'm going to factor this out. A 2, it just makes it skinnier. So actually that second equation here, I'm going to, put in red again. So when I go to graph this, I'm going to move it down 2 units and make it a little bit skinnier because of the 2 in front. So that multiplier makes it skinny. So just to kind of speed this along, that red graph looks like that. But I'm going to keep it in the version that it was given to me. And then label the blue one as well. And like before, we're trying to find this yellow region in here. Okay. Now, in terms of y, we have one right function, right? The blue function is entirely on the right of the red function, which is entirely on the left. And again, I just have to figure out where they intersect at. So I'm going to go ahead and set them equal to one another. So y squared equals 2y squared minus 4. Subtracting y squared from both sides, I get 1y squared. And then I still have minus 4. And then if I factor that, I get these symmetrical answers, which is good because that's what I see in my graph, right? It looks like these guys intersect maybe down here at -2. If I was more robotic in my drawing, they probably would intersect down there. And then over here at +2, they should probably, you know, intersect better up there. So my graph, since I'm doing it by hand, doesn't always perfectly match, you know, of course, what I get algebraically. I would trust my algebra over my graph any day. So if I'm going to do this setup, and I'm going to do right minus left, I'm going to do -2 to 2, and I'm going to do the blue function minus, and then again in parentheses, the 2y squared minus 4. So if you miss those parentheses, you get this question wrong, right? And we don't want that to happen. So that's the case there for number 7. And then one more time, if we do right minus left, this is a little bit more complicated of a function. X equal y to the 2/3. It is that seagull graph, just turned on its side. X minus y equal to 2, I would probably graph as x minus 2 equals y, just kind of switch sides where the y and the 2 are. So I kind of have a y equals format. So y equal to x minus 2, of course, looks like this, pretty much. And then y equals 8, hopefully you remember from the other day, that is a horizontal line. So I am actually, all right, got to draw this a little bit farther to get up there. I'm finding all of this space in here, okay, with one integral. Now, if you did this integral in terms of x, it would take 1 to 3 different integrals in terms of x. That is insane. But since we're doing it in terms of y, it's only going to take one integral because I have one right side function and one left side function. I have lots of different ceilings and floors if I was thinking of it in terms of x. So that's a very useful thing. Now, what I need to find is this green intersection point down here. I'm going to assume that is -1, just because if I plug in -1 to both of those graphs, or if I plug in, I guess, 1, x value of 1, the y value is -1. Sorry, I'm just doing that in my head. Yes, that works out. So they intersect down here at -1. And then again, now I have a horizontal line as my upper limit. So 8, even though that's the function y equals 8, that's going to be my upper limit. Okay, so again, those are the y values. And then I'm doing the right-hand function, okay, which is this blue guy. Now, this blue guy can be represented in lots of different ways. That blue function is x minus y equals 2. Earlier, I turned it into y equals x minus 2 so I could graph it. And unfortunately, right, the version that we need is we need to solve it for x equals, right? So I'm going to take and add 2 to both sides. And this blue function is actually y plus 2, right, when we get it equal to x by itself. So in x equals format, this is the function that I want to put in my integrand. I am not allowed to put anything in my integrand that has an x in it because I'm doing right side minus left side, okay? And then I'm subtracting. My red function this time is just y to the 2/3. I don't need parentheses in this case because it's just a single term for that function. And that is my setup for this last one. Okay, and then to preface what you're going to see in Delta Math, I kind of have stole a problem from there. So this says, let the region R be the area enclosed by f of x equals 3x to the 1/3. So this guy here is 3x to the 1/3. I'm going to trace it in red. The horizontal line y equals 3. That's this guy. Okay, and the y-axis. So the y-axis, let's trace that in green over here, and keep in mind the actual equation of that is x equals 0. So we're going to do this 2 ways. We're going to do it in terms of x. So there's 2 problems here for the price of 1. So it's asking us for the limits, right, to be entered in each box. And then the integrand, of course, you're going to type in, or in this case, we'll write it in the first box. So number 1, because that is in terms of x, right? I'm looking at the differential at the end there. It says dx. So that means I'm going to do ceiling minus floor. And my x1 and x2 have to be x values. Okay, so I'm going to do orange function as my ceiling, right? So that's 3. And then minus my floor function, that is the red one, which is 3x to the 1/3. And since I'm doing this in terms of x, that's okay to use x in my integrand. My left-hand limit is 0. Actually, I'm going to use these colors here. So I'm talking about this intersection point right here, this 0. And then it goes over to this second intersection point right here at 1. So I'm going to put 0 and 1 in here. And then again, that is number 1 up there, 3 minus 3x to the 1/3. Now, if I do this in terms of y, I am going to do right minus left, right? Or window minus wall. Okay. So now my limits are going to switch. I still have 0 because it's at the origin, right, for my lower limit. But now I have a y value of 3 for my upper limit. Again, I'm choosing the purple y values here. And then now I'm doing right function, which is the red guy. Okay, now they gave it to me as y equals 3x to the 1/3 power, but that's a no good. I need to turn that into x equals format in order to put it into my integrand here for number 2, right? So I'm going to divide y by 3, right, both sides, and then I'm going to cube everything. And then that'll give me x equals y over 3 cubed, and that is the function that I can input as my right function, the red one, and then minus my left function, which is just 0, kind of anticlimactic there. That's the green one, and then that's my setup for number 2. So 0, 3, and then hardest part is kind of getting used to only putting y in your integrand for right minus left scenarios.